In this section, we'll talk about suffix arrays, which are a modification, if you like, a simplification of suffix trees. And we'll see how they eventually will be able to replace the suffix tree and be a little more a lightweight alternative to suffix trees, but offer the same kind of functionality eventually. So the goal is to put our suffix trees on a diet. Here's another time a suffix tree, and it's for this string banana band that we've seen before. So it's the same suffix tree, just drawn slightly differently. What I want to point out is for each node, I paid attention to sort the outgoing edges alphabetically. And that was done on purpose. In the suffix tree, there's no real order on the edges. It's a tree, right? So they could go either way. It's just up to us how we draw it. But for now, for this section, I want to insist that the child links are drawn in alphabetic order. If you allow me to do this, and at each and every node in the suffix tree, you notice something convenient. If you read the leaves top down, they appear in sorted order as the strings. It's the suffixes in lexicographic order. And so what about just getting rid of the tree and only keeping this order of the suffixes around? It turns out that's the suffix array, and it turns out that's enough for a lot of things, even though it might look like you're throwing away a lot at first sight. So the idea is we only store this array. And remember that this array is really just an array of numbers. We don't actually store the suffixes as strings. We store the starting index. But one step back. If we don't have the tree, let's do a simple check if we can still do something useful. And what was the first non-trivial thing we did with suffix trees? Finding a pattern in a text for which we have the suffix tree. So let's try to do the same thing if we only have this sorted list. If we're looking for a pattern like Anna, what can we do with the sorted list? Well, we can do binary search, okay? And so that's the approach that we can take here. So if I do binary search, I would probably start comparing in the middle. Now, did I round up or down? Not so clear. Maybe we start comparing here. So I compare this text and Anna. Because Anna stops early, this one compares bigger. So I would go up, right? I'm trying to find the insertion position of Anna. So I would jump into this half. Then the middle would probably be this one. N and the dollar, so dollar comes before all the characters. Notice that I put this here before all the characters, so we have to be consistent. So this one comes before Anna. So we have narrowed down the search range to this one now. Yeah, probably should have excluded this one here, which means I should have compared it to one further up to follow our code. And now Anna is bigger than that because, sorry, it's smaller than that because it stops early. So you can imagine that Anna is also terminated by a dollar. So here we go up and, oh, sorry, this is a ban. So I was talking gibberish. So this one comes before Anna. So we narrowed it down to these two. I would compare with this one, and dollar comes before. So I would narrow it down to this one. Then I compare with that one. And Anna stops early, so I would go up. So I found the insertion position here. That's where Anna would have been inserted if I wanted to include it in this list. That's what binary search gives you. Okay. Now we could do a second search for Anna and with a different dollar letter, I don't know, pound, which comes after all the characters. So you search twice. You search for the pattern with a termination, a dollar symbol like before, that comes before all the other characters, and the second time with one that comes after all those. And in that case, you would find its insertion position here. So two binary searches give you two positions, and the range between those two positions is special, because that range, every pattern starts with Anna, every suffix. Oh, go away. Anna, Anna. So we found all the occurrences of Anna, and is even slightly more convenient. We found a compact representation of all those matches, because we found a beginning and an end index in the suffix array where all those occurrences start. Okay, so it's even slightly more convenient than in a suffix tree. Okay, all matches of P in T. And so we're back to exact matches, right? Forget about the approximate matches, that part's over, at least for now. So I can do two binary searches in the sorted list of suffixes, and that gives me the occurrences of a pattern in the text. So we can still do something useful even though we threw away most of the suffix tree. We just kept the sorted list of the leaves. And so if we do that, if you analyze this algorithm that I just sketched you, we need log n plus 2. That's just the worst case comparisons between the pattern and one of the suffixes. And each of these comparisons takes up to m symbol comparisons, because I have to compare strings character by character. So that's the cost for doing one binary search, and we do two of them, so you multiply by a factor of 2. But so you can still find all the occurrences in, so we can still do pattern matching, string matching in m times log n time. That's an n. Log n is not constant, but it's way better than n, so this is still very useful. And there are tricks to improve on this, but let's for now stick with the simple one. Okay, I said this before, but let's officially state it again. That thing is the suffix array. It is the starting positions of the suffixes as they appear if you sort them lexicographically. And it happens to be, if you have the suffix tree around and you draw its outgoing edges with the alphabetic order, then it is the order that you see the leaves. The more conventional way to draw the tree was top down, and then the L array would be written from left to right, finding the leaves in left to right order. So that's how you would normally see it drawn. Yeah, that's a suffix array. Let's see what you can draw in conclusions from this definition. Again, an awfully long list of statements, so I'll probably have to give you a minute. Interesting. But works now? Yes. Good. I'm sorry, guys, I started the wrong question, right? Sorry. That was one later. We haven't talked about the inverse suffix array, have we? That's the one I wanted. Well, you're very confused. Well, not so much. I mean, this is what I wanted. Well, you did reasonably well on the other stuff, even though you didn't know what we're talking about. Another way of saying my teaching has no impact, right? I'll go by the other implication that you're just brilliant. All right, numbers are creeping up. It looks like many people are done. So I'll leave it open, but I'll show you the answers. And there were quite a few, right? Not all are correct, but everything got some votes. It's a tough one. Let's go through those. Indeed, most are correct indeed, so. Right. What can we say about the suffix array? First of all, L is indeed the list of starting indices that are written in the leaves as you see them if you go from left to right in the tree. If you draw the tree like every normal computer scientist does with the root at the top and growing into the ground, well, we got used to that, I guess. And then the leaves come left to right. This is essentially the same as this, just with the last part changed. So let me say the correct thing and don't repeat the wrong one. If you want to go to the rth leaf in T, the rth from the left, so first, second, and so on, or well, 0th, first, second, and so on, then you will see the suffix starting at position R, so at position L of R in the path from the root to this leaf. Okay, maybe let me say this again. If you take some rank R, that's the position from the left of the leaf you're looking at, some leaf here, it starts at some position I, but it is the rth from the left. Then L of R gives you I, and I is the starting index of that suffix in the text, which means text starting at that position until the end, that's a suffix. That's what you see from the root down to this leaf. Okay? That was what we said before. If you take the suffixes and you sort them lexicographically, you get them in the order that they appear in L. So L0 is the index, starting index of the smallest suffix, L1 is the next, L2, L of 2 is the third, and so on and so forth. You can use the suffix array by binary search to find patterns. This one is a little tricky, and I smuggled in to make it a little more clear. If the alphabet is constant, it's quite clear. Even in the suffix tree, you would only need at most sigma pointers for each node. So it's still the space is linear in n, well, in general, n log sigma is doable with some disadvantages. And that's the same for the suffix array. It also needs space n. But the difference is in the constants. The suffix array is just a list of numbers, whereas the suffix tree is this pointered structure where each node has sigma pointers in the simple representation. And so it's a much bigger constant factor. And even if you play with this, you don't get this completely down. But if you just look at big theta classes, the two aren't different. The space is the same for those two. So that's why sometimes these asymptotic notations are useful, but you have to take them with a pinch of salt. They are not an exact representation. This ignoring constant factors is sometimes not good enough. Okay. So we know what a suffix array is. The list of starting indices in lexicographic order of the suffixes. Leaves us with the question how we can compute them. If we know the suffix tree, I just told you if you draw it the right way, all you have to do is traverse the suffix tree and note in what order the leaves appear. But we started this section trying to avoid to build the suffix tree in the first place, so that's not really that useful, but it's doable. The other option is we reduce the problem from this complicated tree on strings to just sorting the suffixes. Sorting is something we know how to do, right? So you could just do literally that, construct all the suffixes of a tree, of a text, and sort them with whatever sorting method is provided by the programming libraries. The downside is that comparisons now are not a constant time operation, but they can be quite expensive. You have to compare strings by comparing them from the beginning to the first differing positions. And in weird cases, like if the text is all A's, then you would potentially need a linear number of comparisons, simple comparisons for each comparison which of two strings is lexicographically smaller. And so that would be even worse than the simple way to construct a suffix tree. So that's not that great. At least in the worst case, it's not an option. But we can do better in various ways. We'll look at two things. First is a better method for sorting strings. And the second is specifically suffix sorting. So the first thing is really generic for strings, and you could use it to sort an arbitrary list of strings. So it, in a sense, would have belonged into Unit 3, but I felt it's more useful here where we have a use case for it. And the second is really exploiting that we're not sorting an arbitrary list of strings. These are exactly all the suffixes of one text, and that will help us at the end. But let's first look at this because I think it's insightful and is actually quite good in practice. There's still some worst case problem, but you don't often see this unless you run on a text like this. So that as a caveat up front. If the text is like this, don't use the next method. For any reasonable text that doesn't completely repeat itself all the time, the method on the next slide might be a very simple to implement and useful way to compute the suffix array. And if you have to sort strings in general, use the next method. It's almost always pretty good. The method is called fat pivot radix quicksort. That's a mouthful. But let's just do an example and you'll see what it is like. It is like Quicksort, so let's recap that just very briefly. You have a list, you pick a pivot element, and you rearrange the list into smaller than the pivot, bigger than the pivot, recurse. Now we do the same with strings, but what we don't want is compare all the characters, do comparisons that completely settle if one string is lexicographically smaller than another. because that was expensive. So instead, what we'll do is just look at one character at a time. So here's a list of strings chosen so that it has some non-trivial common prefixes. That's our list. In the first recursive call, we pick a pivot string, but what we really look at is only the red characters. I hope you can make out the color that these are red and these are black. So we only compare the first character of each string. And so S is our pivot. And we split this list into 3 parts, not 2. There's the strings whose first character is smaller than S, strictly smaller than S. And there's the strings whose first character is strictly bigger than S. But there's also all the strings, quite a few in this example, whose first character is S. And these go into a separate segment in the middle. Okay? Now, the crucial thing that makes this algorithm more efficient than the other alternatives we discussed before is in this middle segment, I know they all start with an S. I don't have to compare this in the recursive call again and again. Instead, I remember in this recursive call, start looking at the first character. I promise you they don't differ before that. Whereas in these segments before and after, they happen to coincide in the first character, but we don't know that yet. And these don't coincide. So a recursive call now is a range of the array and a number telling you at which index you start comparing, which character index. So let's see the next recursive step. Here we have a small list. We pick a pivot. We partition according to the first character. Nothing really fancy happens here. There's one string that's smaller, and there's one string that has this first character. These are all just singletons, so there will be no further recursion. For the middle list, we pick another pivot. I always pick just the first pivot. You really want the random one in practice, but that makes the example nasty. So here we pick she, but we look at the second characters this time. And the second characters of all those strings. Then we'll have quite a few strings that have a second character that is smaller than h. We have quite a few that have h as their second character, and one lonely one that has a bigger character than h. Okay? And so again, we recurse on all the lists that are not just a single element, remembering what is the character we look at next. In this part, smaller than h, we still have to look at the second character because they might have different ones, except that in this example they don't, but that's something we don't know yet. Whereas here, all these strings start with sh. No need to compare that again and again and again. In this one, something funny happens. They all go to the middle segment and we don't make any progress. We don't split anything up. But we have excluded this first character from the further consideration. One more recursive step. Here again, they all have an e, so nothing really happens. They stay together, but we've excluded e from the consideration. In this one, we have a few strings that have a character smaller than e, for example, L. Okay. Did I want to pick another pivot here? Oh, sorry, I should have checked the third character. No, these are, sorry, I confused myself. So the pivot is E, and it's the third character. So you have to look at these ones. There's 3 strings that have an E as the third character, and these all go here, and then we go to the next character because their E is all the same. Good. The slide's correct. I was mistaken. And there's one string that has a third character bigger than E. That's the O. For the last one, again, nothing really happens, but we get rid of one more character. I think you see how this goes. Shall I fast forward through the example? So another round where we have things smaller and equal. And same here. So you see, for some, you keep comparing for quite a while, and especially in this case, these 2 strings are the same, but the algorithm will only find out by moving through all of the recursive steps and keeping them in the middle partition all the time. So this is not the end of the example. This part would recurse 4 more times or 5 more times before it reaches the end. One thing you may have noticed, whenever a string was actually finished and I needed another character to compare with, I smuggled in a $sign. But it just occurred in this point. So it's just a way of saying if the string is over, you just make it compare smaller with the next character than all the actual characters. Okay, that's how this works. So again, in a nutshell, it's like Quicksort, but you keep also track of which character to next compare with, and you make 3 partitions, not just 2, where you have one for all the elements that are equal to the pivot. That's why it's called fat pivot, because you make this big partition in the middle that has all the duplicates of the pivot element. So how good is this? If you want to read a few more details about this, look at the book or the videos from Sedgwick and Wayne. They discuss this algorithm in a bit more detail. That's just explaining how the algorithm works in general. I think I've done this. Now, the interesting statement is let me circle this to make it really, really stand out. If you apply this sorting algorithm on a list of random strings, where random means each character is just generated according to some distribution and independent of the others. That's not quite what we have for suffixes of a given text, and is also maybe not quite what you have for English language text, say. But under this simplifying assumption, you can show that this algorithm essentially takes as many symbol comparisons as standard Quicksort took for normal comparisons. So this fact that you sometimes have to compare these long middle partitions, that you have to keep going with these 2 seashells, that's just very, very unlikely if you have random strings as an input. And so that's that said. If the strings do have some common prefixes, we at least make sure that we never compare these twice. So in a sense, the algorithm is still doing almost as well as is possible in this case, because a sorting method, if it's given arbitrary strings, it will have to find out which strings have a common prefix to sort them. So it's a good algorithm to sort lists of strings, and it's quite efficient for many types of texts to suffix sort. But it is still not the end of the story for us, because the worst case for suffix sorting is still quadratic. And you get this for, again, our boring text that just consists of A's all over. If you think about the suffixes for this text, they will essentially always fill the middle partition, and just one is split off each time. So you compare all those, and it's inevitable if you just apply a string sorting method. As long as you don't take advantage of the fact that the list of strings are suffixes, you will not get away from this worst case. But I promise you we can do it with linear worst case running time by taking into account that we're sorting suffixes.